Thank you. Thank you. I was going to wait, and I knew that was coming. And I was like, wait till that recording in progress sound happens before you start speaking, so you won't get cut off mid-sentence. Thank you very much for inviting me. I know I'm a little bit of an outsider in this particular community, so I'll try to have this talk as mostly high level, trying to advertise problems that hopefully that some of you folks can help us with, and try to advertise techniques that maybe things that we commonly use that might be useful in your particular problem. I've already seen a couple of those coming up this week. I'll try to speak with you guys when I have a chance to do this. This is joint work with these three other folks. The U.S. government wants everyone to know that that this doesn't reflect them whatsoever. Although, this is actually true. This stuff I'm going to show you, like there's proofs and stuff. So as a person, I'm telling you this is correct, but the government's like, no. So I'm going to try to iterate this from the perspective of compressed sensing. Okay. I do not do compressed sensing. I do matrix design problems that feed into compressed sensing, but I know enough of it to hopefully speak intelligently about it. What I'm going to give you is just Euclidean space, d-dimensional real space or complex space. So F to the D, where F is either R or C. I'm going to give you a bunch of subspaces of that. So like in the example that Emily was showing that we'll go back to here, maybe I'll have 5 subspaces of 5-dimensional space. Those two numbers don't have to be the same, but they will in that example. And they're each 2-dimensional. One thing that you'll see throughout all this, though, is there's going to be some over-completeness. So if I actually had 5 2-dimensional subspaces, you would think that they could span at most a 10-dimensional space. They're actually going to be living in a 5-dimensional ambient space here. And so they're going to depend upon each other. Typically, if I had that scenario where I had sort of linearly dependent subspaces, and I chose a vector from each one of those subspaces, and then added them up and produced to you their sum, and said, okay, given the sum of these, can we go back? The answer would be no, that's impossible. Because of the fact that they linearly depend upon each other, I couldn't tell you what the individual elements of those subspaces were that you used to sum up to produce this one. Well, in compressed sensing, it's a slightly different problem. What I'm going to have is I'm not going to pick a vector from all of the subspaces, or more precisely, I'm not going to pick a non-zero vector from each of them. So you have many subspaces of this one Euclidean space. I am going to pick a vector, a non-zero vector, from a few of those. I'm not going to tell you which one of those few I'm going to pick from. I am then going to add them and deliver to you the sum, and then ask, from that, could you work backwards to figure out what the actual subspaces were, what the individual vectors in each one of those subspaces are? Can you solve this sort of underdetermined linear system subject to the additional information that your solution is very sparse, that you're not picking vectors from all of the subspaces, but only very few of them? That number that I'm going to have is K of them. And then there's several variations of that question, which is like, when could you do that mathematically? Like, when is it mathematically possible to solve that problem versus when is it like feasibly to do that? Like, you would actually want an algorithm that would be reasonable to implement in time, that would be robust against noise, et cetera, to actually solve that. So the problem I more focus on is the design problem that feeds into this, which is if someone were to produce either the real or complex numbers for me, tell me D, the dimension of the entire space, R, the dimension of the subspace, N, the number of subspaces they want. I'll review all these on the next slide. I want to design the subspaces. I want to say, you've given me these design parameters, almost like a combinatorial design problem, sort of a hidden space version of that. I want to produce these subspaces so that when you go through this problem, that you can actually solve it as efficiently as possible, where the K is as large as possible. And so then notation, D is the dimension of the big space, N is the number of subspaces, R is the dimension of the subspaces. Emily, this summer we were joking, I know you like to get mathematical tattoos. We also use these particular numbers in our literature quite a bit. Please do not get DNR tattooed on your body. That means something else. I don't know if you can, at least in America, that means do not resuscitate. If you have a heart attack and you have that tattooed on your body, they're not going to try to bring you back. They're just going to let you sit. All right. So in here, what I'm going to do, notation-wise, and you said I can use the board. We have some chalk. Great. Thank you. Don't need the board too much. But what I'm going to try to do is I'm going to take these matrices, phi1, phi2, all the way up to phi(n). Each one of these individually you should think about as a tall, skinny matrix. Each one of them individually is D by R. And I want each one of them to be an isometry, which is just a fancy word for saying that I want its columns to be orthonormal. So what you should think about is that the columns of this matrix form an orthonormal basis for the first R-dimensional subspace of D-dimensional space. The columns of this one form an orthonormal basis for the second R-dimensional subspace. I'm going to stack them all next to each other. I have n of them all together. And so I am getting a D by NR matrix. And what I want to do is I'm trying to design these subspaces so that this particular problem, this compressed sensing problem of being able to recover the sparse solution to this underdetermined linear system is particularly nice to solve. And so what I'm really going to do is I'm going to think about designing this particular matrix here. So again, it's a D by NR matrix broken up into these chunks where each one individually has orthonormal columns. So the columns of this matrix are orthonormal to each other. The columns of this matrix are orthonormal to each other, but the columns of this and the columns of this are not going to be orthonormal. In general, it's not going to be possible because this is going to be a short, fat matrix. But what we can do is we can sort of compare the two subspaces. Like if you give me any two of these, so if you gave me subspace 1 and subspace 2, and you wanted to ask the question, well, how similar, how much alike are they to each other? And one way to compute that is to take this thing that's called the cross-gram matrix between the two. So again, you have tall, skinny matrix, which is basis for this first subspace, tall, skinny matrix, which is basis for the second subspace. Take the adjoint of the first one, multiply those two together. And so what you get is a small R by R matrix, which really contains all of the inner products between the basis for the first space and the basis for the second space. You can do that for any two of these subspaces. So you have like n choose 2 of these cross-gram matrices to actually compute. And we have this quantity called block coherence. I'm going to motivate this a lot more on the next slide. But what this actually is you take all of those things, all those sort of like tables of inner products between bases, you take the induced 2 norm of those. So you take the largest singular value of all of those, and then you take the largest one over all pairs, okay? This is something that is called the block coherence. Actually turns out it's not a property of the subspace of the bases that you've chosen for the subspaces as much. It's actually invariant with regards to one's choice of basis. It actually just depends upon the subspaces themselves, because basically if you changed bases for the subspaces, it just introduces unitaries on the outsides of that product, which don't affect the singular values whatsoever. But then we have this quantity. Now, the reason there's 2 things in the literature that relate to this. First one is going back to what I was talking about on the first slide, which is again, you have a bunch of subspaces, you're picking vectors from some of them, adding them up, and then pretending like you forgot what those original subspaces were. Could you actually recover what that information was? Could you solve the underdetermined linear system subject to the fact that you were only picking vectors from a few of those subspaces? And the answer is, yeah, you can actually do it, provided this block coherence, this quantity I was just talking about, is small. So this K here is measuring how many of those subspaces you can pick a non-zero vector from before you actually choose to add them all up. I would like K to be as large as possible, basically. That means, from a practical perspective, that I can sense more complicated signals, ones that have greater support. I pick vectors from more of those subspaces before I add them up. So I want K to be as big as possible. There is this bound. And numerically speaking, the bound seems to be pretty tight, pretty good bound. And so it seems to reason that you would want to make this quantity here, this block coherence, as small as possible. There actually are algorithms in this case where this bound is true to actually recover what it is. A popular one is called block orthogonal matching pursuit. Because I think we got the time, it's worth for me just to explain this briefly. So yeah, suppose I did. I had all these subspaces. I pick vectors from some of them. I add them up. I produce that sum to you. And you wanted to know, well, where did that vector come from? You probably don't want to just go through all possible things. I have n subspaces. I maybe even tell you that I only chose non-zero vectors from k of them, and I added them up. If n and k are even moderately sized, doing n choose k possibilities is just prohibitive from the point of view of anything practical. The algorithm, block orthogonal matching pursuit, which is not mine at all. It's really Joel Trop as the first real theorems on this, and this is the generalization of his work to the block case that I'm focusing upon here. What you do is you say, take that sum and then project it on each of the subspaces. You actually do have the subspaces. Figure out whichever one of those projections is the largest, okay? Find that, take that, subtract it off of what you were given. So take the sum, subtract off its projection, the one that's sort of onto the subspace that captures the most of that particular vector. And then you basically repeat the process. Now I have to be a little more precise. Once you take that difference, you then project it onto all the subspaces. You figure out which one of those projections is as large as possible. And then you take those two, and then you do a linear least squares problem at that particular point. You discard the approximation you had in the previous step, and you said, and then you find a linear combination of something in this subspace and this subspace, which is as close as possible to the sum. Subtract that off, repeat the process at that point. But it's now implementable, quickly implementable. You can find that it's robust against noise, etc. So there is actually a practical way of solving what seems like an otherwise impossible problem, but it all depends upon your block coherence being small, and more precisely, the smaller this gets, the more complicated of a sum you can decompose in this way. Yes?
So if I understand correctly, like you're doing some sort of almost greedy approach, right? I have no idea, like, why does it give you the correct answer?
Yes, it is not at all obvious. And when you read through Trop's paper, it kind of goes through those details. And the same thing I asked when reading his paper the first time about, like, why in the world is it going to work? And the proof is really beautiful. I am not prepared to present the details of the proof on this one here, but there are a number of key ideas in that are sneaky. And it's why this one is cited several thousand times. But it's not, I can try to present it in the questions afterwards, but he has like an intermediate concept in between this one and this one, but and some other bounds that basically show up, but it is not obvious, far from it. Yeah, it is impressive whenever someone can prove that a greedy algorithm is actually producing a truly optimal result. And that's exactly what he did in this case. Because of that, I, like inspired by this, and our community is trying to design subspaces so that this quantity is as small as possible. But then reality sets in. Like if mass matrix here is short fat, which is really the case that we most care about this, when NR is bigger than D, then you can't choose all of these subspaces to be mutually orthogonal to each other. That would be the optimal solution if NR was smaller than D. But you can't in the cases we most care about. And there's actually a classical bound about how small could this get. So again, I want to drive it to be as small as possible in order to make K large, but there's a lower bound on what it can be. This is in the case where R is 1, when you're talking about lines, this is traditionally called the Welsh bound. Okay, although it even goes back to Rankine in the 1950s. There's a precursor for it. So it's a very classical bound. Conway, Hardin, and Sloan in the mid-90s did a version of this where this 2 norm was replaced with the Frobenius norm. I'm kind of hybridizing their proof and Welsh's proof in order to get this here, where the first time I think I've seen this expressed as concretely as this is a paper of Calderbank and co-authors from around like 2015 or so. Although I think if you went back in time and asked Joel Trop in 2006 if he knew this, it would be definitely yes. And if you read his dissertation, it would be like, yeah, it's in there. So the important thing is I want to make block coherence small. At the same time, there is this lower bound on block coherence. And for the rest of the talk moving forward, the last thing I'm going to say, and this I can show you, but I don't have the details in here, that you get equality in this bound if and only if you have this very special type of object that I'm going to explain on the next slide called an equi-isoclinic tight fusion. So I am going to take this matrix that I have right here. This is what I'm calling phi. Just basically concatenating all these different orthonormal bases for these different subspaces with each other. And then I'm going to take the grand matrix. So I'm going to take, all these different bases here, take the conjugate transpose, so I put them all as rows, and then just multiply the matrices together, matrix product. And I'm going to get this big block matrix that has as its subblocks the cross-gram matrices that I was talking about before. So down the diagonal, I'm going to get the identity, because if you think about it, I have like the basis for the first subspace, and then I multiply by its adjoint, and those are orthonormal bases. So down the diagonal, I'm basically getting all the orthonormal bases multiplied by their own adjoints, and they're all i's. On the off diagonal, what I'm getting are these quantities that again sort of measure how much overlap there is between the two different subspaces. And it's precisely those off-diagonal entries when I take their largest singular values, so the two norms. So take the two norm of all of these off-diagonal entries, and then take the maximum of those over all possible entries here. That's what we call the block coherence. That's the thing we're trying to make as small as possible. And we achieve that bound that I had on the previous slide, the Welsh bound. We make that block coherence as small as possible, if and only if that these fees that we're talking about have two properties. And I'm slightly oversimplifying this for you because it's a mistake on my end. One of which is that it's tight. Now, what tight really means, I guess I'm doing this so I can write this out. What tight really means is that when you take phi star. So you have this short fat matrix, and then you multiply by its adjoint on this side, you get the unit products of the rows of this guy with each other. When you write that out, it's a sum of the projections onto the individual subspaces. And being tight means that this is some constant multiple of the identity. I've expressed it instead in terms of the Gram matrix. Now, this thing that we call the frame operator and this thing called the Gram matrix are the same product in a different direction. So their singular values are identical up to some zero padding. And so what this is really saying is that this Gram matrix, this thing that has all the overlap information between the subspaces in it, is a scalar multiple of a projection. Is basically the simplest way to think about it, an orthogonal projection operator. It's clearly self-adjoint, but what this is really saying is that its eigenvalues are A and 0. And if you scale it by A, then what you get is something that has eigenvalues 0 and 1 would actually be a projection. Technically, if I just had this on this side, I wouldn't know what the multiplicity of A was. To make this slide correct, I should have also said, and A has to be this number. So that's one property that you need in order to have minimal block coherence. In other words, optimal for this block compressed sensing problem. The second property you need to have is this property that, as far as I know, goes back to Lemons and Seidel, were the first ones to really talk about it seriously in early 70s, which is that you have subspaces which are equi-isoclinic. Now, if you haven't seen this before, and I'm giving you an expression of it, it's saying that all these off-diagonal blocks are a common scalar multiple of a unitary. But that's not a very natural geometric understanding of what this actually means. When you see equi-isoclinic, it's like equal, and it's like, why are you telling me equal in two different senses? Well, these things are equal in two different senses. And what I mean by that is, well, for example, here, when I take this example, I have one R-dimensional subspace of D-dimensional space and a second R-dimensional subspace. Even though this is very hard for us to visualize because we kind of grew up in a 3D universe, okay? Unless we're going to meet like aliens hidden in the crowd, just snickering at all of my dumbness in this. I have a really hard time visualizing four-dimensional space. But if you really did have higher dimensional intuition, if I give you two R-dimensional subspaces of D-dimensional space, there are not just a single angle between them, there actually are angles between them. They are called the principal angles between those subspaces. And one way you can compute them is to actually take the bases for the two subspaces, take this cross-Gram matrix, which contains all the inner products between them, and take the singular values of those that particular cross-Gram matrix. Because each one of them is an isometry, the cross-Gram has a singular value of at most 1. And so all those singular values are between 0 and 1. And they can all then be expressed as the cosine of some angle between 0 and pi over 2. So there's a lot of angles between them. So if we're thinking in four-dimensional space, what I'm really claiming is when you take two planes, there are two angles between them. And it is possible for those two angles to be the same angle. And when that happens, you say that those two subspaces are isoclinic. That's equal in the first sense. Now, these guys, in order to have this property, they have to be what's called equi-isoclinic. So imagine, as in the examples I'm going to have coming up when I go on this next slide here, I'm going to have 5 two-dimensional subspaces of 5-dimensional space. So between any two planes, there are two angles, but there are also 5 choose 2, which is what, 10 pairs of planes. So there are 10 pairs of planes and each one has 2 angles between them. To be equi-isoclinic, I need all of those angles to be equal. It seems extremely restrictive, so restrictive that you might think that such a thing might not exist except in trivial cases. And the remarkable thing about the universe we live in is that they actually do. Non-trivial examples of these guys are actually out there. And they happen to be living inside of objects that people in this room understand much better than I do, like DRACKNs, for example. Okay, that's what I'm going to try to explain to you. When both of these things hold, which if you're not in the graph theory community, DRACKN is distance regular antipodal cover of the complete graph. And so I'll be defining those in an upcoming slide as a generalization of a strongly regular graph. When both of these properties hold, when you have again that this matrix here is basically a scalar multiple of a projection, and all the off-diagonal entries, they're all a common scalar multiple of a unitary, then you get what's called an equi-isoclinic type fusion frame, and it turns out you have absolutely no choice for what the scalars actually have to be in this case. So again, it's a lot to digest. It's a very complicated definition. Here's an example of a grand matrix of equi-isoclinic type fusion frame of 5 subspaces in 5-dimensional space. Each one is actually 2-dimensional. You don't like I'm just trying to give you an overall sense of the pattern here. The main thing to identify is that there's 4 types of matrices. I'm going to show you just numbers in just a second, but there's definitely identities down the diagonal. And then on the off diagonal, there's basically things of 3 different types. You might see 3 different color patterns showing up. Here are the actual numbers. And I should point out there's a global 1/2 sitting out here. So if you actually look here, I've spaced it so you can see the block structure a little more clearly. But if you look here, there's a 1/2 out front, so that I actually do have identities down the diagonal. So I do actually have 5 isometries. One thing that is very not clear about this matrix is that if you squared it, you would get a scalar multiple of itself. If you squared that particular matrix, you would actually get 2 times itself. That you couldn't actually really see unless you actually did it. It's a very rare property. What that's telling you is that this matrix is actually twice a projection, okay? Its eigenvalues are 2 and 0. And if you take the trace, well, you have 5 2x2 identities. So the trace is actually going to be, what, 10? And so if the eigenvalues are 2 and 0 and the trace is 10, then you actually know the multiplicity of those eigenvalues. They have to be 5 and 0. So even though this looks like it might be something involving 10-dimensional space, the eigenspaces in question here are 5-dimensional. And so this is actually the grand matrix of vectors living in 5-dimensional space. And what's happening on the off diagonal is you're getting 1/2 times these matrices. They don't look great, like this is 1, 0, 0, -1, but that's a unitary. This guy's also a unitary. And that's what I'm claiming. That's the properties we actually want. We want a scalar multiple of a projection matrix that has this block structure. We have identities down the diagonal, where on the off diagonal, we're all getting a common scalar multiple of a unitary, of some unitary matrices. The scalar multiple projection, that's tightness. The common multiple of unitaries, that's the equi-isoclinism. When you put the 2 together, that's when you achieve equality in the Walsh bound. That's when your compressed sensing performance is as good as possible, just to carry back to that. Now, you might be looking at this and thinking, dude, I just want this matrix to be a projection. So I want its square to be a multiple, I want this to be a multiple projection. So I want its square to be a multiple of itself. But I have this constant diagonal. It might be better if I just subtract the identity from this whole thing to be able to get rid of that term. And if I subtracted the identity from this term, I might be able to then multiply the result by 2 to actually just get something that had, instead of having identities on the diagonal, had blocks of zeros on the diagonal, and on the off diagonal had unitary matrices. You can do this. Seidel did this. This is what's called the signature matrix of an equi-isoclinic type fusion frame. And so anytime you have a matrix that has these 4 properties, you can work back to one of these objects that's optimal for compressed sensing. What you want is an array. So you want like a block matrix. You want it to be like an n by n array of r by r matrices. You want 0 blocks down the diagonal. On the off diagonal, you want unitaries. You want this matrix to be self-adjoint. And then you also want that when you square S, you get something that looks like some scalar times S, some plus some scalar times the identity. In other words, that the minimal polynomial of S has degree 2. If you have one of these guys, there's an if and only if here. If you start with an EITFF and you define a matrix in this fashion, you get a signature matrix from it. But conversely, if you had a signature matrix, you could figure out this scalar B. It depends upon the rank of or the multiplicity of the two eigenvalues of S. But you could basically recover the Graham matrix of an equi-isoclinic type fusion frame from this. So basically, you boil the problem of designing these matrices that are optimal for compressed sensing down to this design problem of making these signature matrices. This is not the only way to approach to build equi-isoclinic type fusion frames. There are other situations where it is much more convenient to try to build the individual isometries right from the get-go, as opposed to working with the Graham matrix. But for both approaches, there are constructions that work out better with one than the other. Either way, you can turn anything made with one construction into the other format and vice versa. But there's a large amount of literature that approaches this problem from the perspective of trying to actually design a signature matrix. In the special case where R is 1, when the subspaces are just lines, what you have in that case is the signature matrix. These little R by R blocks that I'm talking about are just 1 by 1 matrices. And so you literally just have a self-adjoint matrix that has zeros on the diagonal, plus minus ones on the off diagonal, and has a characteristic polynomial of degree 2. In other words, only has 2 eigenvalues in that case. One thing that's immediate here is that if you have a signature matrix, you can take its negative, and that's going to be a signature matrix as well. What this implies is that equi-isoclinic type fusion frames never show up as a single. They always show up in pairs. One we call the Nymark complement of the other. Basically, you can start with one, take its signature matrix, take its negative, which basically turns the 0 eigenvalue into the non-zero one, and vice versa, swaps the roles of those two, and then go back to having the EITFF. So if I take that example I did before, and I want to look at its signature matrix, the main difference here from what I had before is that where before the diagonal had identities, now it has zeros. Cool. All right, so here's just the numbers. Notice I have zeros on the diagonal, and I got rid of that 1/2. So I literally just have 0 blocks. I got unitaries on the off diagonal. And this guy, when you square it, you actually get a multiple of itself plus a multiple of the identity. This particular one, when you square it, you actually just get a multiple of the identity. All right. There are some simple ways, if you give me an EITFF, that I could make another one. Well, the first one's not so simple. In the case where R is 1, you have this special class of things called equiangular type frames. So they're sort of the special case of this where I'm trying to come up with optimal collections of lines. And Emily gave us a number of nice examples of those in her talk. So those are sort of primitive versions of what we have here, not the only primitive ones. And primitive in the sense of they're good to make other examples with, not in the sense of that they are easy to find. They're actually quite hard to find. But if you gave me one of these objects, an equi-isoclinic type fusion frame, whether R was 1 or not, it has something called the Nymark complement, where this is the thing where you take S and you change it to minus S. You have the same number of subspaces, and the subspaces have the same dimension, but the ambient space is actually changed. Another thing that you can do, sort of a generalization of a tensor product trick, is that you can direct sum to EITFFs, but they do need to have the same proportion of dimension of subspace to the dimension of the entire space in order to actually do that. Notice the M does not add in here. You have a certain number of subspaces, you have to have the same number of subspaces here, and the thing you produce has the same number of subspaces. You're not changing the number of subspaces. What you're just doing is adding the dimension of the subspaces and the space in which they live. There are also complex examples of these and real examples of these. And Hogar has a classical trick for being able to, he didn't talk about tightness, but it generalizes to a scenario. He definitely talked about equi-isoclinism. That's what this paper is about. And you can take a complex equi-isoclinic type fusion frame and convert it quite nicely into a real one by basically representing each complex number in its Graham matrix as a real matrix in the natural way. Where are we at? And by I mean me, I'm in my research community. We're looking to understand these things better. We want to characterize when they exist as much as possible. So what are necessary conditions upon their existence? and what are constructions of them, and try to meet there in the middle as much as possible. It is very much like an analytical version of a combinatorial design problem. Like if you think back to like the 70s, 60s, people had things like vivids, like balanced incomplete block designs and stuff like that. Here are some strong necessary conditions. Here are some explicit constructions. How close can you get them in the middle? I don't believe we're going to get a clean answer for that. We basically want as many constructions of these things as we can actually find, because we can actually deliver them to actually solve this problem and hopefully build better sensors in the future using them. So the stuff that we would really like, even though it's becoming harder and harder to find these, are new equilibrium type frames. The special case of this where R is 1. Now, we actually had a talk yesterday that actually talked about a new equilibrium type frame, a real one. It was of 66 vectors in 33-dimensional space. As Emily pointed out, real equilibrium type frames are equivalent to a special class of strongly regular graphs, and it was Oleg Gritsenko's talk, or a paper, very recent, that actually produced a new strongly regular graph. They were saying that one actually did show up on the table of strongly regular graphs, right? When Brouwer updated this earlier this week, I believe he turned a yellow to a green because of that. Gotcha. And so also non-equivalent ETFs because of that exact correspondence between these. And so new ETFs are still being found. We've still also been finding new infinite families of them, even in recent years. There's also been a recent push on the quaternionic version of this. And Hogar has a version of his trick of turning complex into reals. You can also turn complex into, or quaternionic into complex, and then turn that into reals. And that's why I kind of sighed when the octonions came up earlier today, because there's also, which we jokingly call the octonions because it's fun. There's also an octonion version of this that we've tried to get going. Emily in particular has tried to have some success there, and it's tough because you don't have associativity. But anyway, there's push to generalize the number systems and use that. What I'll be talking about for the rest of today is Chris and his student. I actually have a way in their paper that we didn't fully appreciate until recently of constructing these using DRACKNs and representation theory. Other ones that don't really fit into combinations of existing ones and these kind of like simple tricks are Et-Taoui and some co-authors have a version of Hogar's trick where they kind of represent a complex number as a 2x2 matrix in the natural way, but then they twist it and they kind of stay inside of the orthogonal group, but they leave the special orthogonal group to do this. And it turns out that this produces Equi-isoclinic type fusion frames in ways that are producible other ways by other approaches. There's some other stuff. Emily in particular has a really nice paper producing a few more examples from the quaternions in a different way than these earlier talks or these earlier papers. And I have some other stuff with this group of authors that I'm speaking about that we'll get into. Not from Octavius. Okay. Yes. All right. So I know everyone in this room, well, most people in this room understand this a whole lot better than me, but this is the definition of a DRACKN, which I'm here, I can ask the question, who actually came up with this wonderful acronym? Because the concept has been around for like 30 years. That's me. Because I was like, because I remember the first question I think I asked is like, we were reading the paper, this paper, our group was reading this one. And we were like, man, I wonder if they pronounce it as DRACKN, because if it is, it's so cool. And John and Dustin for a while had a generalization of this that they really wanted to call Kraken, but they ended up not doing it because they released the Kraken at some point. But anyway, it's great. It's really clever because you got distance regular and antipodal cover, but then using KM, the normal abbreviation of the complete graph, as that. And the idea here, when you read Godsil and Hensel's paper, if you look back at like this type of object, they have this exactly in their paper, and they refer to it as sort of like an orthogonal cover of the complete graph. And what I mean by this is, well, there's a complete graph on 5 vertices. If I looked at its adjacency matrix, it would have a 1 in all the off-diagonal entries and a 0. And if I was to cover that, I'm just going to basically say every place there's a 1, I want to put something. And the question is what do you put there? And if you put an orthogonal matrix there, you get an orthogonal cover like we have here. And you might instead put something more general, a larger graph that might be distance regular and antipodal. And if you look at these axioms here, they look very similar to the ones I had for a signature matrix. I have zeros down the diagonal. On the off diagonal, before I had some sort of orthogonal matrix, a unitary matrix. Here, what I'm going to have is a permutation matrix. I'm going to have symmetry, and in the previous case, I had self-adjointness. And for the signature matrix, I had that the signature matrix, its minimal polynomial is degree 2. So that when you squared the minimal polynomial, you get a constant multiple of itself plus some constant multiple of the identity. Here we're going to have constant multiple of itself, constant multiple of the identity. This has to be this. You can argue by counting. But then there's this last term here. Okay, and you need this last term. What this is really telling you is that, and I really read the paper and internalized it. And you can see that by the fact that I changed the spelling of fiber from British spelling to American spelling. So we're going to partition this graph into fibers where each fiber consists of these vertices. There's a perfect matching between any, I'm going to go through an example in just a second, two distinct fibers in a common, distinct vertices in a common fiber are a distance 3 apart. That's part of this antipodal property. And other non-adjacent vertices, ones that are not in a common fiber, have C common neighbors. So here I'm writing this as a permutation matrix. So this is a 15 by 15 matrix. A white means 0. Red means 1, so we can turn to that if you want, but I think it's easier to see the pattern here. And what you have are 15 vertices broken up into 5 groups of 3. And between any one of those groups of 3, none of those 3 are connected to each other, which is why we're getting blocks of zeros down the diagonal. Meanwhile, between any 2 distinct fiber, there is a perfect matching between the 2, which is basically to say, hey, like in this particular one, vertex 1 is matched with vertex 1, but vertex 2 with vertex 3, and vertex 3 with vertex 2 of the 2 fibers with each other. So every one of these off diagonals is a permutation matrix. It turns out that when you have that quadratic condition that I was referring to, some really nice stuff combinatorially happens with each other. In particular, the diameter of the graph is going to be exactly 3. The vertices that are as far away from each other as possible, in other words, 3 apart from each other, are exactly going to be the ones in a common fiber. These fibers are equivalence classes. And the really difficult property to get is that this distance regularity more generally, which you can boil it down here to just one condition, that when you take 2 guys from different fibers that are not adjacent, that they have a certain fixed number of neighbors in common, that number is called C. When you turn this into numbers and then you square it, you actually notice that you get 4 times the identity, but on the off diagonal, you're getting these constant blocks of 1s. And that's really this property here, that on the off diagonal, you have to get constant of J's, where J is an all 1 matrix. So it's a very nice class of graphs. And basically, the axioms feel very similar to the axioms for a signature matrix. And so you might wonder, could you somehow take this type of object and turn it into an orthogonal cover that might be the signature matrix of an EITFF? And of course, the answer is yes, because why else would I be talking about it? And the answer is yes, because it's in Chris's and Hensel's paper from 30 years ago. And if you actually read through it, Chris, I think we were at a Charleston meeting and you pointed me to this paper, and I was already aware of it a little bit, but there's a second section in there. There's one section where you talk about equi-isoclinic subspaces, and then you go and talk about something else for a while, and then you come back to equi-isoclinic subspaces. And if you look into this paper, this formalism is present, this way of trying to actually find tall, skinny matrices that actually give you orthogonal bases for the subspaces. And you talk about tightness in a way that I don't think was present in Lemons and Seidel before. They had a bound on the number of equi-isoclinic subspaces. And you guys were able to prove that achieving that bound was equivalent to some other property that we in the frame community now call tightness. But I think in the literature, it might be the first time the definition really appeared without that particular terminology. So kudos. I'm here to thank you for that. It's nice. One thing as an old mathematician, I really like to get the literature straightened out, because there's always precursors to what we did. And like I said, with the Welsh bound, there was precursors back to the 50s as well. So it's good for us to keep all of us informed about where this all came from. It all has a long history. All right. So, of course, there's an answer. And what you want is a machine that turns permutation matrices into orthogonal matrices. And that machine is representation theory. So this is are re-expressing of your result here, Chris. So what you do is you take the off-diagonal blocks. So you take this DRACKN, you take the off-diagonal blocks of it, they're a bunch of permutation matrices. Well, the permutation matrices, they generate a group. In this particular case, they generate the dihedral group of order 6, which happens to be the same thing as the symmetric group of order 6. But the construction I'm showing you generalizes to the dihedral setting rather than the symmetric group setting. You take that group, you take a representation of that group. There's some terminology that goes on here. It is important that the representation you take does not have the trivial representation as a constituent of it. That's sort of like what you have here is this is itself a representation of that particular group. But because of the fact that it has the trivial representation of a constituent, when you square this matrix A, you get this other term. And basically, by taking a sub-representation of that representation that doesn't have the true representation in it, that eliminates this particular term. And what you convert the matrix A into is an S matrix that simply has a quadratic relation that it satisfies. In other words, the signature matrix of an EITFF. In a special case where they generate an abelian group, what you get out are equiangular type frames, which came to my attention in 2016 when a large number of the authors of this paper were in this room, and that's the first time I learned about DRACKNs. All right, so just in this particular mechanism, there's the DRACKN, there is permutation matrices. Here you can think about it as group elements. So I'm actually writing things as members of the symmetric group in that case. Notice they're all transpositions, okay? And then what I'm going to do is I'm going to turn those transpositions, it's the dihedral group in this case. There is a natural representation of the dihedral group as 2x2 matrices, as just symmetries of the hexagon. Represent them in this way, and what you get is the signature matrix of an equi-isoclinic type fusion frame. Now, Chris, what we didn't see in your paper, and I don't know if you followed it up, so, and we haven't written any of this up just yet, so please help me figure out the literature, is applying this as a machine to crank out infinite families of equi-isoclinic type fusion frames. Because to actually apply it as a machine, you need a construction of a DRACKN, you need to figure out what group it lies in, and then you have what groups the off-diagonal entries actually lie in, and then you need a representation of that particular guy. And of course, there's always one. You can always project onto the complement of the trivial representation. But sometimes you get even fancier EITFFs if you project onto sub-representations of that. And there's this very nice construction of a DRACKN by Mathen that uses a symplectic form over a finite field. And what you get in that case, this is the example I've been showing you this entire time, is that all the off-diagonal permutations all live in a dihedral group. They're all just regular shifts composed with like a flipping, a reversal operator. And the dihedral group has such nice understood representation theory that when you apply it, you actually get an EITFF of Q+1 subspaces in a Q+1 dimensional space where each one is 2-dimensional. So in particular, if you pick Q to be 4, Q is a prime power here, not a prime. If you pick Q to be 4, you get the 552 I was showing you. And then you might ask, as Emily was bringing up, is this actually a new EITFF? Well, there are other ways to produce EITFFs with those exact same parameters. We don't know yet whether they are genuinely new or not, whether they're equivalent in the sense of what you're talking about. So it's good to have tools to help us be able to do that. But basically, there is a technique for turning a conference matrix into one of these objects as well. It's got to be complex and symmetric, which is a weird combination. I mean, symmetric in the sense that it's transposed, not its Hermitian transpose, equals itself, but it's still complex. And you can actually push the theory through this, where you can take the DRACKN, turn it into the EITFF, and pull back through that other machine to actually construct examples of complex symmetric conference matrices through this. And a lot of us in the frame theory community like to think of EITFFs as sort of a mathematical middle ground, that they're just not algebraic objects. There's a lot of different ways to get there. And so sometimes you can connect what would otherwise seem to be disparate areas by taking an object, turning it into an EITFF, and then going back, for example, going from this guy right to a conference matrix. And so we did this, and we're like, are those conference matrices, for example, new? And I think they would have been new about a year ago, but we have a separate way of constructing ones of that same size very, very recently. And we're trying to see if our way of building them this way from this other paper and this way are actually the same or not. This is my last slide. So future work in here, and this is what I'm really trying to advertise to you folks, in terms of help. We only understand the DRACKN literature just a little bit. Again, there's a whole process. You need to understand DRACKNs, you need to understand what group they actually generate, you need to understand the representation theory of that group well enough to push this whole thing through. But if you can, what new EITFFs can you folks deliver to the community? We'd be very interested in seeing them. It's a publishable result. For context here, Gardner, which I think, as far as I know, this is a runoff, where this is an isolated DRACKN, that there's a 761, and if you apply this machine to it, you get an EITFF with those parameters, and that is the only explanation I know of for the existence of that equi-isoclinic type fusion frame. There's nothing else even with those parameters that's out there in the literature. And you construct new DRACKNs from existing EITFFs. And in particular, we have a result kind of, I didn't write this down, but inspired by this paper here, where you guys have a result where if you could construct an ETF where the grand matrix had all prime roots of unity, you could build a DRACKN from it. And we use that machine, we in this group of authors I'm talking about, use that machine to produce a new infinite family of DRACKNs. And now it's like, can we keep doing that with this? We believe that, for example, if there is a complex symmetric conference matrix where all the entries are prime roots of unity, then a new DRACKN would have to be there, or assuming it wasn't explainable by other methods. And just more generally, EITFFs are so much about group theory and unitary matrices that it's becoming clear to the field that we don't understand representation theory as much as we need to. And so that's what I've been doing for about the last 3 years, is just studying representation theory sort of nonstop. And we have more examples coming up in the literature of all that stuff. Anyway, thank you so much. Questions?
Yeah, so when you apply your parameter machinery, so that's 2775, does it give, so you're saying then you've done that and it's not related to anything that's known?
Yes, yeah, if you take Nymark complements or other.
That 761 is coming from the Austin graph.
Okay.
The top. Your 531 is the line graph, the Peter graph, by the way, this is the Austin graph. So your next group, that's the, so your next choice would be the more graph.
I see.
Cover 57.
Okay.
Yeah. No. It isn't if more graph exists. And so unless you have a proof that more graph exists. Announcing a new result. It's not known whether it exists.
I see.
And for example, it is known for the Orthogonal group. It's all complicated. That's the story. You can answer.
So that's not my first place to go.
It's an interesting example.
Yeah. I should note that there are spurious equiangular type frames that are similar that come from the Leech lattice as well, like of 176 vertices in 22-dimensional space and like 276 vertices in 23-dimensional space. There are spurious SRGs that then, correspond to spurious ETFs. So a spurious EITFF would not be shocking to me.
Lemons and Seidel construct, they look at this particular case where the subspace is half the dimension. And so, they construct three, they construct 4 planes in R4. That's the Hurwitz-Radon equation. They construct 6 4-dimensional subspaces in R8, 10 8-dimensional subspaces in R16, and so on. Are those examples, the original examples, interesting to you?
They are. And I didn't know about them until I submitted a paper in December and got savaged. They're like not knowing about these things. And they're like, hey, you're listing them all. And I'm pretty sure it's not you, Bill. You won't be this mean in a review. But there's right ways to reject a paper. And I don't know, I'm just asking this question. Yeah, that's right. But we were made aware, and that's what Joey and myself spent all summer working through those. And we've been able to generalize the construction to the complex case. We have some nice, so we have some infinite families of them. Yeah, that's exact. All those ones are tight. It turns out, so they're all EITFFs. They are interesting to us. And what we spent a lot of time doing this summer was computing their symmetry groups, actually, of them. They all have an enormous amount of symmetry, which is pretty interesting, because when you get to equiangular type frames, you think about which ones are, for example, totally symmetric. And it turns out that the only collections of lines that are equiangular type frames that are totally symmetric are orthonormal bases and regular simplices. But for the case of equi-isoclinic type fusion frames, that's not the case. There are non-trivial things that are totally symmetric, which in some of them occur in four-dimensional space. So there are objects in four-dimensional space that would appear as symmetric as a simplex would be to us that we don't really understand very well, we'll say.
So wait, totally symmetric, you just mean the symmetry group is SN?
Yes,
Yeah.
so that if you rearrange the subspaces, there is a unitary and a change of basis for each one of those subspaces so that you get the exact same grand matrix.
So maybe to say that it's for lines, it's stronger than that, right? It's if you have strictly transitive symmetric group, and it's changes either.
That's right. Yeah, for lines, even if you're triply transitive, you have to be orthonormal basis or simplex because the triple products are constant, basically.
Thank you.
Yeah, no, so it's a great question, and we got stumped by it on a review, and that's why we spent this whole summer making ourselves undumb.
It looks like their constructions are just, from the Hurwitz radon equations and just.
That's
popping up, right?
And part of what we did was they give you a grand matrix formulation. We gave the short fat version of it. And so what actually happens is these things are twice, these D is twice R, and you put a scalar multiple of the identity over the scalar multiple of the solution, something involving the Hurwitz equation below it. So that they have a very nice, it's even simpler than what Lemons and Seidel explained it as.
Just a quick question before break.
That's the theory in the break.
Yeah.
I'm really interested in matrices when they have two distinct eigenvalues, the ones that you're describing. So if you have the matrix, is there any way of finding out whether it can be obtained from your instructions, or like, is there any way of reversing all those?
If you have a matrix that has two eigenvalues, yeah. So what I would do is I would take this in a pseudo real, assume we got like a self-adjoint matrix or something like that, and I would make the smaller eigenvalue. I would add a multiple to the identity to shift that up to 0. And then the other multiplicity would be, and I would then take like a singular value, decomposition of that guy, write it as like a short fat in that particular case. And that's how we typically do that. But then the properties of that, the columns of that short fat matrix are determined by the off diagonal entries in that matrix. So if the original matrix you started with, they're all equal modulus, or they're all broken up into chunks where they're all unitaries, those are the types of things we're interested in. Is matrices that have only two eigenvalues, that they have this additional property that when we push back to this machine leads to something that means well-packed subspaces.
We can thank the speaker again.
Thank you.